Right, well, thank you very much. Alan just told me that I have only 2 hours, and if I go beyond that, I'm going to lose my alcohol card for the reception. So I guess I'm the barrier. The ticket, that's right. I guess I'm the barrier to the reception. All right, so I'm going to tell you today about our work on what we call quantum membranes. And as the term says it, there are really 2 components to this. There's the quantum part. We're dealing with materials that are very thin. So quantum confinement plays an important role in the band structure, transport properties, and we're dealing with membranes, films that are weakly coupled to the substrate. So they're not necessarily covalently attached to the substrate. Before I give the talk, I'm going to acknowledge my students in postdoc. We're a group of about 30 students and postdocs, and the stuff that I'm going to talk about today, none of it was done by me. It was all done by the students and postdocs that are listed, specifically the ones that are listed in bold. They were the ones who did the work. I have to acknowledge the funding source. The work that I'm going to talk about was funded mainly through 3 different funding agencies, different aspects of it. That includes E3S, the Least Center at Notre Dame, and also Intel. And I also have to acknowledge all the collaborators that we're working with inside E3S, inside Berkeley, and outside. So I thought the previous talk, Sapan did a great job of talking about the various constraints that you have to think about when designing your tunnel transistor. I'm going to add one more constraint, and that's the scaling law. We cannot forget about the scaling of transistors, and all of you are familiar with this. As you scale your devices, smaller and smaller, if you grab a planar MOSFET, you go from a switch to a resistor. So you have severe short channel body effects. So when we are designing our next generation transistor, not only we have to think about the tunneling and controlling the tunneling probability, but we also have to think about the electrostatic issue. The electrostatic issue will govern all future transistors, regardless of whether they're MOSFET or tunnel transistors. And in this regard, there have been really 2 approaches that are taken to reduce the short channel effect. Both are either fully or partly proposed and demonstrated here at Berkeley. One is the ultra-thin body SOI, and the other one is the FinFET. And the general rule of thumb is for both of these devices, for good electrostatics, transistor electrostatics, you have to have body thicknesses or fin thicknesses that are about 1/3 or 2/3 of the gate length. So if you have a gate length that is only 5 nanometer, you have to think about body thickness of only 1 to 2 nanometer. So that's really down to atomic scale thickness. And when you're at that extreme scaling limit, you have a lot of fundamental issues that you have to worry about. The effect of quantum confinement. Does it help you? Does it hurt you? How? The effect of surface roughness, band edge roughness. And we have to think about all of these while at the same time thinking about the various constraints that we have for designing our next generation transistor, for example, a tunnel transistor. So the work that we have done at Berkeley, we have mostly focused on using these membranes that are 2-dimensional, very thin, down to a monolayer for different device structures. And the platform that we have, we call it X on insulator, and X stands for the semiconductor of your choice. It could be a 3-5 semiconductor, or it could be a chalcogenide. And in the case of 3-5s, we have been able to do the scaling down to 3 nanometer thickness. So you have a single crystalline, for example, indium arsenide that is only 3 nanometer thick. In the case of chalcogenides, layered chalcogenides, you heard a little bit from Sapan. We can do it down to a single monolayer. So this is a platform that we have that we're exploring at Berkeley. And a number of advantages or features that we have that are enabled with this approach. One of them is that you're making your devices, you are integrating your materials through a layer transfer process rather than direct growth. So that really simplifies the processing of the materials, the integration of the materials that will enable you to think about new type of heterostructures without having to worry about a lot of the lattice or crystal structure constraints that we often face when dealing with epitaxial growth. So let me first tell you about the work that we have done on 3,5s, and then I will give you the results that we have, some of the recent results that we have on chalcogenides. And the way we make our 3,5 XOI, it's very similar to SOI, but it's here, remember, the top layer is not S, it's not silicon, it's X. It's a semiconductor of your choice. And the way we do the processing is by layer transfer. We start with a 3,5 growth substrate, in this case gallium antimonide. We epitaxially grow a sacrificial layer, for example, aluminum gallium antimonide. On top we put our active layer, in this case indium arsenide. You can pattern the indium arsenide, and then you can selectively etch away the sacrificial layer, release the active layer, transfer it onto the substrate of your choice, in this case silicon oxide. And these are some of the resulting AFM images of the structures that we have transferred. In this case, you're looking at indium arsenide ribbons that are transferred on a silicon oxide. The dark brown regions are your silicon oxide surface. The yellow ribbons, those are your transferred indium arsenide. So we can do this with a high yield. We can do this for a wide range of different material systems: indium arsenide antimonide, and even gallium antimonide base materials. So when we started this work about 5 years ago, we really started thinking about, and actually we really started taking a different approach. Rather than direct growth, we thought about this transfer. And at the beginning, we were criticized quite a bit. We didn't have transistor results back then. And the fundamental question was, first, do you get good interface quality for these transferred films? Your film thickness is very thin. You have all these interfaces at the bottom, on top. What is the interface quality, the DIT? Does it impact your transistor performance? Do you even get transistors out of these materials? And the answer is yes, and I will show you that. And the second question was, we're dealing with very small bandgap materials. We were at one of the funding agency reviews, we were said that indium arsenide is a wrong material system. The bandgap is too small. The bulk bandgap is only 0.36 electron volt, and that's not enough for getting low leakage currents. And of course, the answer to that was quantum confinement. You cannot think about the bulk band structure, but you have to think about the band structure for the membranes, for the materials that you're dealing with, down to the thicknesses that you're playing around with. As a rule of thumb, to the 0th order, you can assume that if a material dimension, for example the thickness, is less than the excitonic Bohr radius, you're in the quantum confinement regime, and the carriers are quantum confined, the bandgap will expand. And if you look at silicon, for silicon, even if you go down to very small thicknesses, the Bohr radius is about 5 nanometer. You're not going to see a strong quantum confinement effect. The bandgap is largely bulk. So the silicon community largely ignored the fact that for some of the 3,5s, for example, indium arsenide, the Bohr radius is very large. So if you thin it down to 2 nanometer or 3 nanometer, and that's what you need to have for future scale devices, the bandgap is not going to be the bulk bandgap. So the question is, how do we probe the band structure, and how do we probe the quantum confinement effects in these materials? One way is to do absorption studies. That's what we did. We did FTIR absorption studies of our material system. In this case, we transferred our indium arsenide to an optically transparent substrate like calcium fluoride. So now you can do detailed absorption studies, and from that you can directly measure your effective bandgap. So these are the results. These are the absorption spectra for our indium arsenide films, starting from 3 nanometer in thickness all the way up to 19 nanometer in thickness. The first thing that you see is that the onset of absorption changes, it moves to higher energies as you decrease the thickness. And that's your effective bandgap. So here I'm plotting the experimental effective bandgap that we're extracting as a function of thickness, and you can see that clearly for a film that is about 2 or 3 nanometer in thickness, the bandgap is about 1 eV. So the bandgap is actually large enough. It's much larger than bulk bandgap. You cannot use bulk bandgap. The other interesting feature that we saw is this is stepwise absorption. And of course, that's expected for a quantum well material system. And this is at room temperature. So this tells us that we have a clean quantum membrane. It is a quantum membrane, and nothing special about it. But what is unique, and this is a work that we did with Eli Jablonowicz, is look at the magnitude of each peak, the stepwise absorption that is due to these inner band transition between the 2D subbands. The magnitude is exactly the same. This step is exactly the same, regardless of which inner band transition you look at, regardless of the thickness, regardless of whether it's 3 nanometer or 19 nanometer. And we were, in fact, able to theoretically show that you do expect that there is something that we call quantum unit of absorbance, which roughly ends up being 1.7%. There is no effective mass in it. You can simplify it. And at the end, the total absorbance ends up being A is equal to M, the number of modes of transport that you, number of modes of transitions, the number of transitions that you have, allow transitions that you have, times the quantum unit of absorbance. So this is very similar to the electrical conductance G, which is equal to M, the number of modes of transport that you have, times GQ, the quantum unit of conductance. So the quantum confinement plays a major role, but you might ask yourself, well, you know, how are the transistors? Can you make good transistors? And the answer is yes. We were able to get mobilities between 1,000 to 7,000 centimeters square per volt second for electrons. These are field effect mobility, not the Hall mobility. Subthreshold swing, look at this. We were able to get down to roughly 70 millivolts per decade by doing proper surface treatment. So we have very high quality surfaces and interfaces. We have low DITs. These are good material systems for transistors. We have also built TFETs out of these. And I'm not going to talk about it too much, but Sapon talked about the bilayer tunnel transistor. And this is an example of a bilayer tunnel transistor. In this case, you have indium arsenide that is homogeneously doped. You put a selective contact for holes on one end, selective contact for electrons on the other end. You have a back gate, you put a top gate, and effectively that becomes your tunnel transistor that Sapon talked about. And clearly you see this NDR effect. One of the criteria that I always set for my students, if they bring the data to me and they say, well, we have a tunnel transistor, the first question that I ask them is, do you see NDR? And you have to see NDR in the forward bias regime. So in this case, the forward bias is actually negative voltage, the way we're plotting it. If you don't see NDR, in my opinion,
I think you have to define NDR.
Negative differential resistance. If you don't see this peak, that is indicative of a Esaki diode. You have a gated Esaki diode here. You have to really think carefully whether you indeed have a tunnel transistor or not. And in my opinion, it's very hard to convince otherwise. 3.5s, as wonderful as they are, we have a big limitation, and that's the thickness scaling. Here I'm plotting the measured mobility of our devices as a function of film thickness. And look at this. As you go down to sub 20 nanometer, you start to hit this valley of death in mobility. And it's for silicon, the valley of death is about a couple of nanometers. Here it's much larger, and the reason for it is these materials are quantum confined. So if you change the thickness just a little bit, the potential profile on the surface becomes very rough. The surface scattering becomes more prominent. And in fact, if you look at an atomic force microscope image of the surface of as-made, as-grown indium arsenide by MBE, you can see that you do have surface roughness at that atomic scale. So there's a fundamental limit to how thin we can go with 3.5s. So that's where we think chalcogenides and layered chalcogenides can come into play. And Sapon briefly talked about it. These are material systems that are very much like graphene and graphite, except they have a band gap. They have an intrinsic band gap. And you have these layered materials. Within each layer, the bonding is ionic/covalent. They are separated by van der Waals bonding. And the neat thing about this is you can make devices down to a single monolayer. There is no native oxide. In principle, there is no surface roughness. So in principle, you can get very sharp band edges. You don't have to worry about the roughness. And there is a whole library of them. Here I'm just plotting the valence band and the conduction band edge of the different chalcogenides that we have available. It's a whole library of them. These are just a few, and you can see that they're all over the place. So you can think about also building different heterojunctions based on van der Waals interfaces. And this field really took off about 2 years ago, or a little bit more than 2 years ago, when at EPFL, Andres Kay's group showed that you can make very good transistors out of molybdenum sulfide. And they were able to show that for a single monolayer device, they were able to get a mobility of 200 centimeters squared per volt second. This mobility may not seem high, but remember, this is a single monolayer. The thickness is 0.7 nanometer. For silicon, for indium arsenide, you will not be able to measure a mobility at such a small thicknesses. So that really took off and created a field. But there was a misconception for a while. After the results came out, people started looking at other chalcogenides, and most of the transistor characteristics were very poor based on other chalcogenides. So for a while, the belief in the field was that moly sulfide is the only good transistor, is the only good layered chalcogenide material in terms of transport, and there were a lot of theoretical studies as to why that might be the case. Our conclusion was that's not the case. In fact, most layered chalcogenides that we have studied exhibit excellent mobility. It's all about contacts. When you have very thin materials, very small materials, contact resistance always dominates. You have to figure out how to contact them properly. Moly sulfide, because of its position of the valence band and conduction band, you were able to, by luck, readily contact the conduction band, so you don't have to worry about the contact resistance. So we started looking at this more carefully. One of the materials that we grabbed was tungsten diselenide. The previous result had shown the mobility is very poor in this material system. It was not attractive. But what we showed is by doping this material properly, by basically having contacts with proper work function, metal work function, but then by doping P plus or N plus regions right next to the source and the drain, effectively by thinning the Schottky barriers, just like what you do with MOSFETs, you can make very high performance MOSFETs. And in this case, you can see that the as-made device, the IV characteristics looks like this. The current is low. If you extract the mobility, which is meaningless, it's very low. After you dope the contacts to P plus, you can now see that the on current goes up by a couple orders of magnitude. Mobility is 250 centimeter square per volt second. This is for P doping. Similarly, you can do potassium doping for N doping. And these materials indeed have high mobilities. So now that we have this library of materials, it's not just moly sulfide, it's really a large library of materials. The next question, of course, is can we think about building van der Waals-based heterostructures? And there are a lot of advantages for this. There are no interdiffusion of atoms in principle. The band edges are sharp in principle. And you can really mix and match. You don't have to worry about the growth constraints or lattice mismatch constraints as long as you do layer transfer. Eventually, we have to think about growth techniques and from manufacturing point of view. But at least at this point, we don't have to worry about it. But there are fundamental questions that need to be answered. The first is, can you get electrically active van der Waals heterojunctions? And the second question is, if you have one two-dimensional material on top of another two-dimensional material system, do they interact with each other? As Stepan said, do you see any wave function penetration between the two materials? Can you probe it somehow? Can you characterize it somehow? And that's what we have done over the last year or so. The first thing that we did was we grabbed our favorite N material, quantum membrane for N-type devices, which is indium arsenide. We made indium arsenide XOI. And we made a heterojunction between this XOI with tungsten diselenide. And if you look at TM, you can clearly see that you have a layered structure for tungsten diselenide at the bottom, and you have indium arsenide on top. And this is the first demonstration of a van der Waals heterojunction built between two semiconductors, and we published it earlier this year. And what we were surprised to observe was that the diodes show a ideality factor of close to 1, about 1.1, for a layered transfer interface. And the reverse bias current is very low. So we have pretty good diodes, even though you have these interfaces that are made by transfer process. So indeed, you can make electrically active junctions with good interface properties. So the next question, an obvious question, was, well, in this case, if you look at the TEM, you can see that these are not very thin. They were tens of nanometer in thickness. So then the next question is, what happens if you start to go down to the ultimate heterojunction limit in terms of thickness, atomically thick heterojunction? And that's what we have done. And we grabbed two material systems among chalcogenides that are now very popular. I talked about our favorite, which is tungsten diselenide, and moly sulfide, which is well established in literature. So the question was, if we build this heterojunction, a single monolayer on top, a single monolayer on the bottom, how does it behave? And what are the intrinsic properties of this heterostructure? So we built these heterostructures, and the first thing that we did was that we did TEM on these material stacks. And here what you're looking at is a single layer of molybdenum sulfide. Here is your single layer of tungsten diselenide on a single layer of moly sulfide. And you can clearly see this moire pattern that comes from a little bit of angular orientation that you have between the two layers when we transfer one on top of the other. And from the high resolution TEM, at least based on this scale, which is pretty small from TEM, you can see that the interface is very clean. We know how to transfer these things pretty cleanly, at least down to this scale. We have to characterize a larger area, and that's why you can see a clean moire pattern between these bilayers. So the next study that we did was looking at photoluminescence characteristic of these heterojunctions with clean interfaces. And here I'm showing you the PL spectrum for a single layer moly sulfide. And you can see that the peak PL signal is about 1.9 electron volt or so. Single layer tungsten diselenide, and this is the bilayer. With the bilayer, you clearly see a change in the PL peak position. So there's indeed a strong interaction between these two material systems, and now we have a new material system with a different band gap. And the way we see this is that, first of all, the band gap is direct based on the PL study. The PL signal is strong, so it's a direct band gap heterojunction or semiconductor. And the optical transition is spatially indirect. So you have this spatially indirect transition from one layer to the next layer. We have gone forward and we have done a lot of various characterization of this heterojunction. One of them is photoemission electron microscopy. You can look at the energy of the core levels and also the work function in various levels and map them as a function of displacement, position. And from that, you can actually get an idea of whether you have any built-in electric field, a built-in potential. And we were able to observe a 2D dipole effectively with a built-in potential of about 400 millielectron volt. The moly sulfide is positively charged. This is a monolayer. The tungsten diselenide is a monolayer, is negatively charged. And this potential difference is 400 millielectron volt that is within a single monolayer, or that van der Waals gap. So the electric field is gigantic in this structure. We can also manipulate the inner layer interaction by putting different insulating layers in between. In this case, we inserted another layered material, which is boron nitride. And again, you can see the PL spectra of single layer moly sulfide, single layer tungsten diselenide, and N0 is basically a heterojunction between the moly sulfide, tungsten diselenide without any boron nitride. N is the number of layers of boron nitride. So that's what I showed you before. And as you start to put boron nitride in between, you can now prevent that inner layer interaction between the two material systems. So we can control the degree of interaction by putting an insulating layer. Finally, the last slide, Sapon talked about band edge sharpness. It's critical. We have this heterojunction. The question is, how clean are the band edges and how sharp the band edges are? So here is the implied absorbance versus photon energy. And from the slope of these lines, you can get an idea of your band edge sharpness. This is a work that we did in collaboration with Eli. And you can see that almost for all three cases, the single layer moly sulfide, single layer tungsten diselenide, and the heterojunction, the band edge sharpness is 30 millielectron volt per decade. That's very sharp. You're dealing with an atomically thick material system. If you have a 3,5 and you make it that thick, slightest variation in the thickness will give you a very large band edge roughness. So this is exciting, and I think this is going to be a platform for us to build on and move forward. We have already we know how to contact these layers that I talked about separately. So we have already made some devices based on the stack that I talked about, and it's a work in progress. And we think that this presents really a new opportunity in terms of engineering new type of interfaces, heterojunctions, based on van der Waals interactions. And with that, I'm going to conclude, and thank you very much.
Excellent talk. It's time for some questions.
I just have a question. You work mostly on the materials with high mobilities, and you show very good mobilities. But in the ballistic regime, we have a ballistic mobility which limits us anyway, So does this high mobilities translate to high uncurrent or?
Well, when we started this project, high mobility was kind of a driving force. And yes, for future scale devices, the on current will not linearly scale with mobility, but it will linearly it will go as the injection velocity, and the injection velocity still depends on the effective mass. So there is an improvement still if you use these high mobility materials, but not as much as you would expect. It's not 100 times improvement or 10 times improvement that we were hoping for. But for the purpose of today's talk, for some of these exotic devices, silicon will not deliver. So you have to think about how to integrate new material systems on silicon. And this is one platform that you can use. There are other platforms as well for integrating a wide range of electronic materials with small thicknesses that you need for good electrostatics on a silicon substrate.
Ali, very great results. And we're also doing something similar. So I'm going to ask a quick question regarding this measurement. You mentioned on this two monolayer stacked heterostructure, and you used X-ray. It looks like some type of microscopic XPS measurements.
That's right. It's XPS microscopy. That's effectively what it is. It's PEM.
Right. So I noticed. I was wondering when you mentioned this 400 millielectron volts. Is that? I just wanted to basically have an idea about the band alignment. So is that the valence band of, so basically the difference between the two valence bands of the two materials?
No. So what we're looking at is, there is basically let's go back to it. The moly sulfide, just looking at the core levels and how it shifts for a single monolayer by itself, a freestanding single monolayer, versus a single layer of moly sulfide on a single layer of tungsten diselenide. By looking at the core level and how it shifts, and because we can do imaging, we can actually get really the exact position, the exact energy level as a function of position. By looking at that, we can tell what's the built-in potential within each layer. So we know it's about 200 millielectron volt positively charged in the moly sulfide. And for charge neutrality, you know that tungsten diselenide then has to be negative 200 millivolt. And in fact, from PEMs, that's the case. So it's one is at plus 200. So it's the effective potential that you care about, and it's 400 millielectron volt.
I see. From the PIM measurement, can you actually also extract the Venus band
Yes.
of that?
Yes.
Yeah, what is it?
Yes. We have looked at that. I don't remember from the top of my head, but we have that as well.
Great, thank you.
So follow up on the your indium arsenide and tungsten selenide, right? Your current density is like microamp per micron square. So what do you expect? I'm just wondering. That seems a little bit low side. For practical applications.
So far we don't know what is limiting the current density here. And what I should tell you is the device structure that we had, it was the junction was vertical, but the contacts are sideways. So you have this long tungsten diselenide and the source contact is here. You have this long indium arsenide and the drain contact is here. It's just we made it like that for the ease of fabrication. So we're not doing the measurement vertically as we should. Ideally, we want to do in the future. Just for the ease of fabrication, that's how we did. So currently, we are really limited by the parasitic resistances of this end and the contacts. And in fact, we have the contact resistance that you get, or the parasitic resistance that you get for a tungsten diselenide device for the same length. And the resistance here for this diode is really limited by those two parasitic regimes. So we are not still at the limit where you're in the, and that's why you see this, by the way, saturation in the diode characteristic. The parasitic resistance is really dominating. So in the future, we have to make devices that are better contacted on top and bottom.
So what's the barrier height here?
This is the band alignment looks something like this. So this is indium arsenide, this is tungsten diselenide, and this is the band alignment that we think we have within our material system.
Two questions. First one is about the example 2. How do you achieve N-type and P-type doping of the die-chuck G line? And the second question is, from you showed that for the heterostructure, you should work clean surface and interface, and from the TM Mori pattern seems very clean and no contamination. So I guess this monolayer die-chuck G line is obtained by mechanical effluation, I guess. So how about make this heterostructure using like CVD grooves die-chuck G line, because that will involve transfer process that will introduce contamination. I think that will cause problem. Maybe.
So let me first talk about your first question, which is about doping. And when you have a molecularly thick material system, so in this case, it's actually not atomically thick, it's molecularly thick, right? It's the thickness of the material it's a molecular scale thickness. You have a molybdenum layer here or tungsten layer here and two selenide atoms. So for a case like this, when the material is very thin, it's now well established that whether it's organics, whether it's a carbon nanotube, whether it's indium arsenide quantum confined, which we have shown in our group, you can use a concept that is known as surface charge transfer doping. And so we employed a technique that was known previously for mostly organic materials and carbon nanotubes to these chalcogenides. And what you do is basically you put a molecule or a material on top that is either electron withdrawing or electron donating. You play around with the HOMO and LUMO levels of your molecule, or similarly the conduction band, valence band edge position of your molecule and the material. By choosing the right combination, you can either withdraw electrons or donate electrons. And in the case of NO2 withdraws electrons from tungsten diselenide because of its HOMO, LUMO positions in respect to that of the tungsten diselenide. And in the case of potassium, in the case of N-doping, we use potassium. Potassium wants to donate an electron, and that's actually very well known. Potassium wants to become K+. So that's the technique that we use. Now, in terms of how to make these heterojunctions, we've been doing layer transfer with the focus on interface for now 5 years when we started the indium arsenide XOI work. And the interface is everything. For substructure swing of getting 70 millivolt per decade, we had to engineer the interface. So we know how to treat these materials cleanly, and we've been playing around with them. And of course, every time it's a little bit different depending on what material system you use. So these are all based on layer transferred the Scotch tape technique. Now, moving forward, ideally, from manufacturing point of view, you want to be able to do this from CVD grown or other techniques, grown by other techniques. That material system is still not available in terms of high quality that yields to high electronic properties. That's still a research area that needs further research and development.
Okay, one final question.
Oh, my question is related to also Sarpan's previous talk. From the experimental result, you measured 30 millivolt per decade in absorption. So I'm wondering whether you have measured, for example, temperature dependent.
Good question.
Yeah.
That's something that we're interested to look at moving forward. We haven't done that yet.
You haven't done that yet. Okay.
What you saw was the room temperature result.
The second question is, have you looked at, for example, the doped layer versus non-doped layer? What is limiting the 30 millivolt per decade? That's basically my question.
So that's a very good question, and I don't have a good answer to that right now. And that's something that we will have to be exploring further down the road to see whether we can improve it a little bit more.
In particular, in terms of this type of charge transfer, doping, ideally, we're not supposed to perturb the HOMO levels and LUMO levels. Ideally, we do not want it to. But I still wonder whether they actually can create the fluctuations of the conduction band edge and the valence band edge, which will create some limitation.
So that's a good point, and that's a big advantage of the surface charge transfer doping. And in fact, we did this for indium arsenide as well, and we presented that as the big advantage for surface charge transfer doping rather than body doping, the substitutional doping. And whether that will help us in terms of band edge roughness, we don't know because we don't have the results, but we think it should because it's not creating those local defect sites. But that's something that we have to look at down the road as we move forward.
Okay. With that, I'd like to first thank all of you.